Okay, let's get started. Um, let's talk about the project real quick because that was fun. Um, let me pull that up. All right, so congrats to everyone for submitting and for finishing this one out. Congrats to 4 second-round picks for getting first place on the leaderboard. Are you here? Anyone? All right, that's a flex. Doesn't show up to lecture, gets first place, walks away. All right, cool. So yeah, congrats to the first team. But you'll notice that at the top here, all the performances are pretty close together. So is anyone in here in the top 5 or in the top 10? Top 10? Anyone in here? Okay. Yeah. Okay. Yeah, congrats. All right. Great. Um, so yeah, I mean, like again, I think this is a I really like this project because it kind of gave everyone a lot of space to be creative and introduce a lot of problems that you will continue to see as you use machine learning on your own problems and research projects and things like that. So I think, again, not to pat myself on the back or anything, but I really like this project. I did want to point out, again, all the kind of everyone's notebooks is now on Piazza, so it is worth browsing through. I think there's some really high quality ones up there. I did pin the top 5 just so you can see what they did for reference, but I'm sure there are more high quality notebooks lower in the leaderboard as well. I just haven't had a chance to go through them just yet. So as I find more good high quality notebooks, you might see your notebook being pinned at the top and kind of cycling out which ones I think would be useful to see. I did want to point out the notebook from the 4 second rounds pick team. I think it's pretty well structured in the sense that the actual notebook itself serves as a sort of a report. So I do think it's worth reading through just to see what they did. In particular, they're showing that the distribution of the different features between the lab and the simulated sets are different, which is kind of intentional. It wasn't supposed to be perfect. And so based on that, they kind of lay out their decision making. This is called SHAP, which uses game theory to determine which features are important. You might have attempted to use like XGBoost's feature importance feature, but those are flawed due to one reason or another. And so they're kind of difficult to interpret. So if you used SHAP instead, you got a better understanding of which features were more important or less important. So that's, we do not have time to talk about all these different tools that exist, but SHAP I think is worth learning because it's very interesting. It's almost like a game theoretic approach to model interpretation. So it almost tells you, which feature was most informative for influencing the final model output. We use this quite a bit in our research lab as well. And then also this other team called WHIP, I'm not sure why, I think it's an acronym or something, actually plotted all the tracks out on a single frame before they started doing anything. And you can notice that on the simulated set, and again, this was intentional, all of the non-modal particles flow in the same direction in a straight line. And all the simulated modal tracks all show very similar kinds of motility, whereas in the lab set, there's quite a bit of diversity in the type of motility that exists. And then, of course, the non-modal tracks flow in a straight line or stay in the same place, but all in different directions, right? So just being able to see that in the first place might have influenced your decision making down the road on whether to use the simulated data set for what reason, et cetera, right? So you'll see a lot of these notebooks, and I think some students are coming in with some experience in data science and machine learning as well. So don't feel bad that you don't know everything up front. There's no expectation there. But you'll see a lot of these start to say, either that, another term you'll see is exploratory data analysis, or EDA. That kind of means before we even touch a machine learning subject, can we just plot everything and see what we get? And then as a kind of a researcher, as a human, you can say, all right, what would I do with whatever I'm given? And then you try to approximate that with a machine learning model, right? That's kind of the walkthrough of working through a project. So anyways, yeah, so again, looking forward to reading everyone's reports. Hope this was fun, and we'll move on to the core lecture content now. Oh, and the homework 5 is out, so you can start working on that. Okay, so before I start also, thank you all for coming to the lectures in person as well. I just want to say personally, it is impossible to give lectures to an empty auditorium. I don't know if any of you have tried, but having people to look at really helps me out too. This is also the first time I'm like lecturing a course. Like I've been a TA before. I've done like recitations, but like this is the first time I'm actually doing like core lectures. So it helps to get your feedback and you like nodding during lectures, like kind of keeps me going on on the lecturing. That said, I did have the misfortune of watching my own recordings. And I do think I tend to belabor the point sometimes. I'll kind of repeat the same thing 4 times before I move on. Or I'll say like, okay, over and over again. So I'm working on that. So, next couple lectures, hopefully I improve. This lecture content I am more comfortable with personally. I mentioned before that lecture 10 was a little rough for me because it was all new content to me as well. So this one should be a little bit more smooth sailing. Okay, all right. Okay, so let's talk about embeddings, which is a really fun subject. And I also have some research background in this. I did some research on this during grad school. So for the past 2 lectures, we've talked about dimensionality reduction and clustering. So we started kind of from the perspective of unsupervised learning, machine learning when you don't have any labels. And then we talked about clustering, we talked about PCA, and then we talked about singular value decomposition, and then we talked about bilinear filtering, SVD-like models, and latent factor models. And so we kind of ran into another problem where we only have labels and no features, and then we kind of saw how that generalizes out into a bilinear model, right? So we've covered a lot in the last couple lectures. This is going to be kind of even a further zoom out of that. So you'll remember that when we talked about latent factor models, a lot of that had to do with learning some low-dimensional representation of data. So in fact, for the multitask learning example, we started with a purely linear model, just the matrix W, taking some X and predicting some Y. And then we showed that by instead representing that as a matrix factorization model where you predict some UV so that you're projecting these X's into some lower dimensional space and then learning a linear model in this lower dimensional space, right? We can kind of generalize better and we can solve some tasks that we weren't able to before by learning this low dimensional representation. So this is the path that we're going to continue to go on, except with embeddings, the whole point is to come up with a good representation in this lower dimensional space. And then that enables a lot of downstream tasks because you can do anything with these features down the road, right? So embeddings, you can kind of represent them as generalizations, even further generalization of latent factor models, right? Latent factor models has this UV structure. We're going to get rid of that as well. We're just straight up learning a embedding. And I do want to say embeddings, this is the most widely used form. So when I talked about bilinear filtering before, I said this is kind of niche. You kind of use it for recommendation systems and not much else, or for like the Netflix problem. Embeddings you find everywhere. Deep learning, traditional machine learning, anything that you do, you will find embedding. So we're going to walk through this, and I really like this structure. So first, and this is going to cover a lot, so I'm going to go a little bit quickly, and you're not expected to, especially the first half of it, you're not expected to kind of understand the very details, because first we're going to talk about locally linear embeddings, and we don't use this anymore. It's definitely not state of the art, but it does kind of explain what the motivations are, where we started, and what the kind of problem formulation is. So it's good from a fundamental / kind of baseline kind of a way. And then from there, we'll move on to probabilistic sequence embeddings, which is a huge field, very important field, especially in NLP, right? And then we'll move on to deep embeddings, which is kind of, it's gotten so accessible now that it's kind of the baseline now. Everyone starts at the deep embeddings and then goes up from there, for better or worse. So this is kind of the structure of this lecture. So again, we're going to start with locally linear embeddings. I'm even gonna skip some slides because Professor Yisong also skipped some slides. So we're kind of just gonna go through it quickly. Okay, so the high-level concept of embedding is that, and you're tired of hearing me say this probably, but we're again learning some representation U that is projecting some input X into a lower dimensional space, right? I feel like I've said that 100 times during the last couple lectures. So where each column U corresponds to some data point, right? And then you multiply U by your input and it spits out some lower dimension vector, right? I do want to mention that in materials, in the literature, columns and rows are used like interchangeably. So depending on whether you're transposing X or not, or whether you define your initial vector as a row or a column, it can be a column or a row. So don't get confused by that. The important part is that some axis of U corresponds to a data point, and then the other axis is the lower dimension representation. Do you have a question there? No? Yeah, okay, all right, cool. Yeah, so, and then what we're trying to achieve is we're trying to achieve some semantics encoded via some distance metric or some similarity metric between U and U prime. And so what we're trying to say here is the embedding that comes out of multiplying matrix U by some input, we're embedding some semantic, some meaning of similarity or difference or some higher level information. So for example, if it's for songs like genre or artist or something like that, we're trying to embed that into the subspace itself, this lower dimensionality subspace itself. And there's two main ways of defining this mathematically, right? So the first one is to just use the Euclidean norm, and we say this whatever semantic we're trying to imbue, right, can be represented as the distance between points, right? So let's go back to the songs example, and then you'll see this later as well. If we say I want some embedding of a song where in embeddings that are near each other are similar songs, right? So similar, whether that means genre-wise, whether that means they're in the same key, right? Whether it means they're classical and it's from the same, I don't know, romantic era, etc., right? Like whatever semantic you decide is important. We want them to be kind of encoded into this distance metric. The other one is similarity, right? So for similarity, we're talking about kind of cosine similarity, right? It's a dot product between two vectors, right? And there is a distinction here, right? The Euclidean distance between two vectors and the dot product between two vectors are two different kind of ways of defining your metric. And we'll see an example of both of these in a future slides. But also worth pointing out that the dot product example generalizes back out to latent factor models. So everything is related, everything is the same. You will never escape linear algebra, right? Everything's a decomposition. So let me see. So the first framework by which we're going to kind of explore this is called a locally linear embedding. And like I said before, I'm going to burn through these ideally within about 20 minutes just to kind of give you this example. So this is the earliest embedding work where this was like a pretty major like science article when it came out, like the journal Science paper when it came out. And this is kind of where this field originated from, and that's where the intent of the rest of this field is kind of pegged on, is this original work. This is also not on the homework Yisan wanted to mention, so don't worry about it. Okay, so given some unsupervised data set X, right, or I guess S in this case. And when I say unsupervised, there's no labels, right? It's just data points in some coordinate space. The way they structured their problem is we want to learn U such that local linearity is preserved. So what does that mean? That means that even if you have some really complex data, right? Even if you have some real complex shape, if you just look at some small epsilon subset of that data, you can kind of estimate it with a linear relationship, right? So if you have a circle, I don't want to draw this out, but if you have a circle and you have a really dense string of points in a circle, if you look at 3 of those points, you can draw a line through those 3 points, right? Like it won't be perfect, but you can at least estimate the relationship between nearby points with some line, some linearity. This is what we're trying to do. We're trying to learn some U, some projection, such that it maintains this local linearity, but we now get to use that to find this lower dimensional representation. And this is also called manifold learning. So I didn't even have to do a circle example because there's a plot right here. But again, any neighborhood in this 3-dimensional data set, right? We have this weird 3-dimensional manifold here that's like curled in on itself. But if I just look at 4 of these squares, it looks like a plane, right? So if I can learn that, if I can learn what this relationship in this plane is, I can then kind of sample these points, and I can say, I want you to make sure that within this small area, the points that are near each other stay near each other, but represented in a 2-dimensional space. So we're learning this manifold, and we're spreading it out in 2-dimensional space, and therefore we're embedding this 3-dimensional data into this 2-dimensional space while keeping the local relationships the same, right? Pretty straightforward, I think. So the approach that we'll take, and I've kind of alluded to this before, is we're going to define this relationship of each x to its neighbors. In this case, in that case, in the example, it's just like spatial distance, right? We're going to define this relationship x of x to each of its neighbors. And then, again, we're trying to find some lower dimensional u that preserves that relationship. It keeps points that are near each other, but still is able to represent the data in 2 dimensions instead of 3. Okay, so let's say this mathematically. So we're going to create some b, where b is the nearest neighbors of some given data point, x. And we're assuming that b is approximately linear. This completely falls apart if you can't assume that b is like approximately linear. If the data point's like a random Gaussian cloud, like this is not going to work, right? We're assuming that there exists some linear structure at a smaller scale. So then, as a part of this assumption, we're now further saying that each data point x can be written as some convex combination, some linear combination of its neighbors, right? So we're saying that any data point can be represented as some convex, some linear combination of its neighbors, right? That's the initial assumption. So showing that graphically, right? We have given some point x. If we define its neighbors, in this case, we're saying 2 of its neighbors. We could say 3, we could say 5, right? That's a hyperparameter that we can set. But given some 2 of its neighbors, we're assuming that data point x can be represented just by a convex combination of these 2 data points, of its neighboring data points. And that's the relationship that we're defining. So, yeah.
How close is it? I mean, is it a hyperparameter for how close it is?
Yeah. Yeah, so you can say, yeah, so there's a couple parameters you can set here, right? You can say how many neighbors, and then you can say you can set some threshold as well. So you can say top 5 neighbors as long as they're closer than some distance metric. Yeah. Yeah, so representing this mathematically at the bottom left, right? Relationship data points. So again, we're just saying that given some x, we can approximate it with a convex combination using w of its neighboring data points xj, where j is in the neighborhood, right? And we're saying this is convex, so we can constrain the sum of all the elements in w to 1, right? So it's a convex combination. We're just constraining the sum of the weights to 1. And we're also saying, I think it's also non-negative, like each of the values in w are non-negative as well. And that's just by definition of convex combinations. Yes, okay. So in this case, we need to learn w, right? We need to learn w from the given data points. So given some neighbors b, we're solving for w now. We're saying how can we define this relationship? We're going to learn it directly from the data. So I'm just going to put everything on the screen. I think that's the last slide. Yeah, okay. So for every data point I and its neighbor, we're trying to learn w such that we're trying to best estimate each point using its neighbors. So we're minimizing the squared loss, right? So I think that first equation is pretty straightforward. And then using some fairly basic arithmetic, and Yisan glosses over this, so I'm going to too. Using some fairly simple arithmetic, we can simplify that expression down to something that we can more easily optimize. So one step that happens is, we move xi into the term, right? Because that's kind of easier for us to deal with. And then it's a squared loss, so we kind of break it out into this transpose, and it's the transpose of itself, the multiplication of the transpose by itself. And then turns out if you define c as this other term, where now we have k, so we're summing over both j and k. So these are like, you can kind of think of these as nested for loops, but within the same neighborhood. We can rephrase this entire optimization term as w transpose c w. That's all you need to know. You don't need to know further than that. The whole point is we can do algebraic manipulation to end up at a new minimization problem that's easier for us. Okay. So yeah, so that term ends up being that term. That seems familiar, right? WTCW. everything comes back in on itself. So again, so the whole point here, and this is going off like the original paper, so that's why I'm kind of glossing over this. But we end up at this new optimization objective, and we need to find out how we're going to solve for W. So it turns out, because of this new formulation, we can solve for W using Lagrange multipliers. So we covered Lagrange multipliers, again, very early in the lectures, like lecture 4, lecture 5, or something like that, when Dr. Reva Pragada was presenting. So Lagrange multipliers is like an optimization thing, right? So if you don't know Lagrange multipliers, you can kind of cover this later. It's not a big deal. The point is that we have some optimization term at the top, but we have this equivalency, right? And so whenever you have some function that needs to be optimized, but you have some equivalency constraint, you can leverage Lagrange multipliers to do the optimization. So because we're enforcing, in fact, so before we said this is some convex combination, right? We said W is a convex combination. We said that each data point is being estimated as the convex combination of its neighbors. Because of that, we can constrain W to sum up to 1, and that's equivalent to constraining the L1 norm of W to 1. And so because we have this equivalency constraint, we can use Lagrange multipliers. I wrote down here that at any local minimum or maximum of optimizing a function with an equivalency constraint, the gradient of a function can be expressed as a linear combination of the gradients of the constraints of that point. If that jogs your memory as to what Lagrange multipliers are, showing that geometrically, it means that we have this kind of loss function gradient, right? That's what the color is representing. And this purple diamond is representing this L1 equivalency, right? So our solution needs to lie on this purple diamond. And it says that the local minimum of this function is represented by the blue, the equivalency is represented by the purple, right? So the gradient, which is represented in yellow, right? The gradient of the kind of the loss manifold as this function needs to be perpendicular to a line that lies perpendicular to the purple line here itself as well. But you'll note at the corner, this gradient can go in any direction here because it's tangent. And so solutions of using Lagrange multipliers as an optimization technique usually tend to be at the corners because it's just a lot more flexible, right? You don't have to be perfectly orthogonal to this line to be the local minima. You can just kind of take any combination of these multitude of purple arrows. So that's kind of a geometric interpretation. Again, if you don't get it fully, it's totally fine. Don't worry about it. Okay. All right. So the point to all this being, we can write out the Lagrangian. We can take the gradient of W of the Lagrangian, and then we can solve this equal to 0 because that's the weight W constraint. And then finally, we can show that W is proportional to this formula here with this previous C that we defined. And apparently that, right, so we can show that this is proportional, and then because of the proportionality, it implies this solution, which is just a normalized version of this original proportionality. So, sorry. So again, I'm just going through this very quickly to show how this was done originally, and showing that we can use Lagrange multipliers to solve for W given some C. I'm just showing that it's possible, right? So just given the data X, we can learn W. That's all you need to get out of that. Okay, so one cool thing about this locally linear approximation about W is that it's invariant to rotation, it's invariant to scaling, and it's invariant to translation. So we can take this and we can do all these transformations to it, and because of all the features that we discussed before, it's totally invariant. And so we can kind of mess with it in that direction, and that gives us a little bit of flexibility going down the road. This makes intuitive sense, right? Even if we take those data points that we had before, even if we rotate them, even if we stretch them out, even if we move them around the coordinate space, it doesn't change the local relationships, right? It doesn't change which points are near which other points, right? So that's all this is saying, is that this W that we learned that represents the local linearity is invariant to all these things because it should be by definition. Okay, all right. So, story so far, we've defined this locally linear embedding task where we started with the assumption that given some data point x, we can estimate it using its neighbors. And then we've optimized for the w that represents that relationship, right? That approximation. It defines that approximation. And we've shown that we can learn w, we can solve for w via Lagrange multipliers, and I hand waved over most of that. So now we have this local linear approximation, but you remember that the whole point originally was to then project that onto a lower dimensional space, right? So we learned W directly from the data points. We've learned the local linear relationships directly from the data points. And now we need to learn how to project that into a lower dimensional space while maintaining that local linearity, that local relationship. So again, from X, we estimate W, and now we need to learn U. Oh, that was this slide. Okay. Right. Okay. And then again, the whole point, and then the way we can write this out is by replacing the x's with u, right? So before we were optimizing, we were finding w such that estimating some point x with its neighbors, we minimize the squared loss, right? Now we're holding w fixed. So before we were learning w from x, now we're holding w fixed, and we're finding some u such that the projected points satisfy the same constraint, right? So before we were optimizing w, now we're optimizing for u, but the same loss function, the squared loss function, where we can estimate any point in the low dimensional subspace as a combination of the neighbors in that same low dimensional subspace using the same w that we learned in the high dimensional space, in the original dimensionality. So, oh boy. I wrote that in all caps, do not go over derivation. Okay, all right, so we'll just go through this. Yeah, so for the sake of time and for the sake of the later topics in this lecture are more important, we're going to skim over this. One thing that we're going to set is that U times U transpose is the identity matrix in the k dimension. That makes it, again, more amenable to future, well, so it makes it a projection matrix is what that makes it. So we saw that before with PCA and stuff. And then, oh, right, and then making the, what is that? Oh, that just makes it translationally invariant. So this just makes it centered around 0, the bottom sum term. So based on that, we can rewrite this. I'm not going to go over where this comes from. You can go back to the slides if you want to go through it theoretically. There's also the paper on this originally. This is from a while ago. This is from like year 2000, I think. So you can go through the full derivation if you would like. But we rewrite this optimization term, and then we get this symmetric positive semi-definite matrix, which means that we can actually show that via some min-max theorem, use the principal eigenvector of the pseudo-inverse of M, which means we can use PCA. And so it comes back to PCA again to solve for this projection. Whatever. Okay. Yes. Okay. So the actual important part is, again, starting with some data set X, we define its nearest neighbors term as function capital B. We compute the local linear approximation, W, that allows us to estimate any data point using as the convex combination of its neighbors. And then holding that W fixed, we now learn the lower dimensional embedding that maintains this W neighborhood condition, but in some lower dimensional space. Okay, and then we can use PCA to solve that second part. Yeah. Yes.
You have to reduce the dimensionality of W when you multiply it by U.
Yeah, that would make sense, wouldn't it? Let me go back. Yes. I am also unclear on that. I'll get back. Let me read the paper and I'll get back to you. Thanks. Yeah, the dimensionality doesn't really make sense there, but maybe we project W itself at some point. Does that make sense? Wij. Oh, you're right. Yeah, okay. Yeah, Wij is a scalar. Yeah, it's just an element. Thank you. I missed that completely. Yeah, so there's no dimensionality there. Thanks. Okay, so let's see some results because this will actually ground it a little bit. Okay, so again, we have this original true distribution. We're going to sample 2,000 data points from this probability distribution. And then we're going to say, we're going to define B as the number of neighbors that we're representing. So if we just represent each point as a combination of 3 neighbors, that's not enough, right? So we just kind of get this, a lot of points overlapping each other and such. But the more neighbors you use, the better you represent this local linearity. And so you can unfurl this kind of 3-dimensional data points in 2 dimensions instead. And then the reason it's kind of squished closer here is because that's at the inside of that curve. So you can imagine that the points are closer to each other because the curvature is tighter, right? And so the points are nearer to each other. And then as it furls out, it spreads out in that dimension as well. So that's interesting. All right, let's actually get into the cool stuff. So for probabilistic sequence embedding. So again, many of you are probably familiar with this already because of NLP and because of large language models, but we're going to start all the way from the beginning, and we're going to kind of walk through it. And we're going to structure this around 2 different examples. The first, we're going to structure it over playlist embeddings. So this is a pretty common problem ever since online services for music became a thing, but they were doing these tasks with radio playlists long before this also. But the idea is that users generate song playlists for free, right? So Spotify has a collection of every playlist that you've ever made. And that we can kind of treat that as free training data, right? So you've labeled songs for Spotify or whatever streaming service for them to learn from. Because they're assuming that each playlist has some commonality within the songs themselves, right? We're not sure what. So some of you might do it based on genre, based on mood, right? There's different reasons we create playlists, but we're assuming that there's some high-level semantic reason that you're combining these songs into a single playlist. And so the question is, can we learn some probabilistic model of these playlists, and can we learn something about the songs themselves by just using the playlists? The second example is far more popular, and it has been in the news lately thanks to ChatGPT, which is word embeddings. So again, we generate so much. I was trying to think of like millions, trillions, probably more than that, right? We just write a lot of text all the time, and then we upload that onto the internet for free. So we can treat the entirety of the internet as our learning set, and we can ask, can we learn some probabilistic models of word sequences, of words themselves, of sentences, of documents, etc. So just based on text already written, can we learn something about the words themselves? So we're going to structure our task, or we're going to define our tasks kind of using these definitions. So first, we have what Yisong refers to as the ground set, also the element set, or if you're doing NLP, the vocabulary, right? So this is the list of all individual songs or individual words that exist. So we have this set. And then we have our actual data set, or this is our corpus if you're working in NLP, which is a list of playlists, documents, sentences. It's some sequence of these elements, right? It's a list of those sequences. And then, for each sequence, we can define them as some ordered set of the elements, right? So we're going to work with these definitions. And the goal is to learn some probabilistic model of sequences. Now, Yisong wrote this on here, but that's because we haven't really gotten to probabilistic models is the next lecture. And it's hard to give this lecture without that lecture. It's hard to give that lecture without this lecture. So we have a bit of a chicken and egg thing. The model that's represented here is called the Markov assumption, specifically the first order Markov assumption, where we say that the next element of a sequence only depends on the previous sequence, right? So what we're actually trying to learn is some joint probability of, how is this? Yeah, sure. What we're trying to actually learn is some joint probability of this sequence existing, right? What's the likelihood that this sequence exists? But as you might know, joint probabilities are like notoriously hard to learn, right, or to calculate, because we need to do like every single possible combination. It's hard, right? And so instead, we want to convert this into some conditional probability because we're better at working with those. So the first order Markov assumption says, the probability of some sequence like of P4 only depends on the previous element, right? And then we can chain this. So that's what a Markov chain is. So we can multiply this by the probability of the third element conditional on the second element, and so on until you end up, you multiply with just the probability of the first element existing. So this is the first order Markov assumption. We'll get there in the next lecture. Okay, so what is the form of P? So again, forget about this for a second. Let's just work on the first order Markov assumption. How do we learn this model? How do we learn P? How do we say if the previous word in a sentence was what's the probability of the next word, right? So one way to do this is just do a lookup table. So look at your corpus. Oh yeah, sorry. Mm-hmm. Mm-hmm. So in this one, we are assuming that the order of playlists is important. And that's a really good point, because if you do like Spotify or Apple Music, like people shuffle through their playlists all the time. But this work was originally done with radio, in which case the order actually mattered. So yeah, so we are keeping the order. Same thing with sentences, right? The order of the words matter. So we are, we're assuming that the sequence matters, the order of the sequence. Good question. Okay. So one way to do this is just with a lookup table, right? So we look through our database, we look through our data set, and we extract every kind of two pair of songs that exist. And then now we can build a conditional probability table where we say, what is this? Start. Okay, so the probability of song 5 showing up after song 3 is 2%, or the probability of song 6 showing up first is 8%, right? We can calculate this table just based on our data set alone. The main problem with this is that the complexity of this is the cardinality of the number of songs squared, right? So we need to build every pairing. And the first order Markov assumption is just first order. There's second order, third order, right? We can say each song depends on the previous 2 songs or 3 songs, and the models get more complex, so it gets squared, cubed, to the 4th order, etc. So the complexity grows very quickly. And also, these tables tend to be very sparse, right? There are some cases where 2 songs have never been played one after the other. Either that means, it genuinely are two, you generally don't want to put those songs back to back, or it means one of the songs is so new that no radio station has really played it yet, right? So this table tends to be kind of pretty sparse. So, hold on. As an outline for sequence modeling, we're going to say, so we're going to talk about these 2 problems, and we're going to, and the reason Yusong chose these 2 examples is because the playlist embedding we're going to cover is a distance-based embedding, and the word embedding called word2vec, which we're going to talk about, is an inner product embedding. And so we can kind of cover both examples, and we can compare and contrast afterwards. But that's why we chose these 2, and this is why we're not just talking about word2vec, because like word2vec is like incredibly influential. So we do want to talk about it, but the playlist embedding will kind of set us up for it, and we'll be able to compare afterwards. Okay, so this particular paper, and so I don't want to present this as some general method that works on everything, right? Now we're presenting the work of a single research paper, which was influential. It was like 400 citations or something. But the way they chose to do this, hold on. Sorry, I'm making sure that I'm not dropping. Okay, so the way they chose to do this is to learn that playlist example of songs, right? they chose to represent this in this Markov embedding of distance. So we're saying that the probability of some song appearing after its previous song, right, is the exponential of the negative L2 norm of the negative distance between the embedding of the previous song and the embedding of the next song, right? Specifically, U and V are different. So each song has two embeddings. It has an entry point embedding and it has an exit point embedding. So we're saying that if we can find some embedding of the previous song, right, and then as the exit point of that song, for that exit point, we can find all the nearest kind of entry point embeddings of other songs, right? And then we're saying that the distance between that, reflects how likely that song is to be played next. I feel like I explained that very badly. Let me try that again. So again, we're trying to estimate the probability that some song will come after another song. We're going to embed that previous song into some lower dimensional space. And then we're going to embed this next song into that same embedding space, right? And then the distance between those two embeddings tells you how likely that is. And then we're just presenting it in this exponential form, because that's what we do. Allows that becomes negative. Yeah. Now the distinction for this specific setup is that we learn two different embeddings, U and V, right? Because we're kind of taking into account that transition between two songs might be not invariant, so not associative. So B coming after A is different from A coming after B. That's what we're trying to encode by learning two different embeddings for the entry point of a song and the exit point of a song. This will make more sense when I show this graphically. There's a graph that comes after this. Okay, so this is proportional. So if you imagine back in the previous models as well, right, this is just a distance. This is not a probability yet. So what we actually need to do is we need to compare this value of this exponential to the exponential of every other song to get the actual probability of this song coming after some other song, right? So we're just this is just softmax, right? So all the probabilities need to sum to 1. That's all we're normalizing for here. So it is proportional, but if you want the actual probability between 0 and 1, you need to divide it by the probability of every other song coming after that song. That's just a conditional probability thing. Okay, so Yisung calls this log radial. No one else uses this term. not to point that out. I'm not saying that's a bad thing. I'm just saying Yisung calls this the log radial function. This will become evident because in the graphs it's radial and it's log, so log radial. But you don't have to memorize that. If you also, Yisung wants to point out, if you squint at this, this is just logistic regression. But instead of a binary logistic regression, it's multi-class. So if you kind of look at the, it's exponential of some loss term on top of the normalized thing, it's just logistic regression. Okay. So again, the important thing here is the scoring function is the distance function in the embedding space. It's that Euclidean distance between the two embeddings. All right. So this will make a lot more sense when I show this graph. Again, so probability of some song appearing after another one. This is the exit point embedding of that previous song. And now the U is the entry point embedding of all the other songs. All the songs that lie on the same circle here are equally likely to show up after the previous song, right? Because again, this distance metric is Euclidean distance, right? So if there's an embedding here and another embedding here, they're just as likely to show up after this song as anything else in that circle. Okay? No, it is continuous. We're just drawing contours for visualization. Yeah. Mm-hmm.
You could do that.
You could. Yeah, you'd lose information for not much gain, but yeah, you could do that. Yeah, it would just be like L1 instead of L2 or something, right? Well, you would draw diamonds instead of circles, actually, if it was L1. I guess you could cast into integer or something. Yeah, there's different ways of doing it. Now, the benefit of doing it like this, so the benefit of working in this embedding space is that per song, the amount of parameters that we need to learn per song, we learn 2 times k. So 2 comes from the fact that we're learning both an entry and an exit embedding, and the k is the dimensionality of this embedding. This is 2D, so k equals 2, but you can imagine this as spheres or 4-dimensional hyperspheres or whatnot, right? And then in total, to learn that, we get 2 times cardinality of S, so the number of total songs in our data set times the dimensionality. So again, this is much lower than cardinality of S squared. So it's a lot less complex to do. So we can solve this problem using this embedding. Let me make sure yeah, okay, perfect. So another way of looking at this is we can kind of interpret this probabilistic transition as some kind of probabilistic reconstruction, right? So we have some sequence of songs. We get the lower dimensionality. We have the lower dimensional representations of each song, and then using some logistic regression model, we're trying to reconstruct the playlists, right? So once we have all of the kind of conditional probabilities built using this method, we can actually start with any song and we can chain it and we can try to reconstruct the original playlists that were in the data set using just the chain of these probabilities, right? So one way to interpret this is as this probabilistic reconstruction of the original data using this lower dimensional representation. And note that I'm not talking at all about how we actually come up with the embedding itself, right? Because we can do just a matrix. That can be a neural network on itself. That actually doesn't matter. The point is the way we're constructing this is so that we're optimizing for that objective function. How you end up with the embeddings is pretty fluid. Okay, so going back to our problem definition, we have the songs, we have the playlist, we have the definitions of the playlist, the learning goal. We're trying to find, and we're using UNV here. So I said before it could be a neural network. Let's just say it's UNV matrices, same thing as the last couple lectures, right? We're trying to find some embedding UNV such that, stay with me, this the probability, so that we maximize the probabilities of the observed playlist. So whatever probability model that we find here, whatever P that we find, it better, so for the playlist that we do have, that we have observed, it better say that they're very likely, right? Because they're true. These playlists do exist. So we want to maximize the probability of those playlists existing in whatever model we define. That's all this is saying. And then we can break that down with the first order Markov assumption by saying for every playlist, right? For every playlist, and then for every song in that playlist, we're maximizing the likelihood that each observed song is conditioned on the previous song in that same observation, right? So we're maximizing this probability on the observed playlist, right? Because we know they exist. And then again, we covered this before, where it comes down to multi-class logistic regression. And one thing we should point out, and does the next slide do this? No. One thing we should point out is this is expensive, right? This bottom part, where we need to normalize whatever exponential of the distance metric we get. This needs to be a probability between 0 and 1, so we need to divide by the probability of every other song appearing after that previous song. That means we need to sweep throughout the entire corpus, calculate this for every other song, and then normalize this value. So that is computationally expensive, and we'll talk about how to deal with that. So this is expensive because the way we defined P again, do I have it here? Right, so the way we define P here is as like logistic regression, the exponent of this, the negative of this distance metric. That's expensive to do, so in order to simplify, and multiplication is also expensive computationally in general. And so in order to simplify this computationally and for our sake, we can convert this maximization of the products of the probabilities into minimizing the negative log likelihood. You will see this formulation over and over and over and over. We do this all the time. This is pretty standard. We turn this maximization problem into a minimization problem by taking the negative log of the probability And because we're taking the log, the products also become sums. And now it's easier, right? That's all we're doing here. And now we can solve this using gradient descent. And we're not going to talk about that anymore because we talked enough about using gradient descent to solve embeddings already. Okay, all right. Oh, I mentioned this already, where we would like to do this, but calculating z is really expensive, and so there are different tricks that we can do to approximate it instead of actually exhaustively calculating this bottom normalization function. We'll talk about this more with word2vec as well. And this paper has the solution that they use specifically for the song sequencing problem, but it's not that important. We'll talk about it more once we get to word2vec. There's a really clever solution that word2vec specifically used. Okay. Okay, so story so far, just to recap, we have the playlist embedding. The task is to predict, given some existing sequence, what the next song is going to be. That's what we're trying to learn. That's the probabilistic model that we're trying to learn. But there's a lot of missing values and such, so we use low-dimensional embeddings of songs, and we learn these low-dimensional embeddings of songs so that we can learn this model, without and also generalize without having to learn this like cardinality of S squared complexity model. All right. Any questions about the song sequence modeling problem that we've presented so far? Pretty straightforward, right? Okay, cool. All right, so for this problem, we talked before about this dual point model where we learn the entry and exit of each song because we're assuming that A coming after B is different from B coming after A, right? Well, so you can get rid of that. And so we can make this problem simpler by just doing a single point model where we say transitions are symmetric, right? So some song A coming after some song B is the same as B coming after A, right? So we don't learn a different entry and exit embedding per song. The formulation becomes exactly the same. Instead of learning U and V, we just learn U, and everything else is identical. But this is easier to visualize because we don't have to, songs aren't in like two locations anymore. It's just in one location. So we can actually end up with this visualization where we can do a two-dimensional visualization of the embedding space, right? So you could do the embedding itself into 2 dimensions and plot that, but then it's not as good, right? You can't really describe the differences between all the songs in 2 dimensions. So we're going to use some k-dimensional embedding for the songs themselves to actually learn the task, but then we can further do dimensionality reduction on those k-dimensional embeddings to generate this 2-dimensional visualization, right? And we can, I think this one used tsne, which is like a pretty popular thing, but you can do this with PCA as well. So this is a further dimensionality reduced just for the sake of visualization. And you can see, again, it's learned that, and these labels are applied post hoc. So the model itself didn't know who the artist of each song was, but just based on what songs were in what playlist, it can determine, it can group songs of similar artists into similar spaces, right? And remember, this is a distance metric. So that's, again, important because it's a distance metric, we can plot this in this kind of coordinate space and similar points cluster together because we're using distance and not dot product. Okay? And then, yeah, and Michael Jackson transcends genres, so he's like spread out, right? But you can see otherwise, a lot of artists are kind of clustered. Okay. All right, so we've talked about this for some given corpus. So but let's say I'm Spotify, and I need to do this for a new song that just came out, or a new playlist that came out. So how do I, oh wait, hold on. All right, I've gotten ahead of myself. Never mind. Let's just talk about sampling new playlists. So I mentioned this before in the probabilistic reconstruction interpretation of this model. But given this conditional model, right? If we have some partial playlist already, I can keep chaining on new songs to that, right? This can become a generative. It's not generative, but we can generate new playlists using this model that we've learned, and those playlists are likely to be higher probability of existing based on what the models learn. Okay, that's all that's saying. All right, now what about new songs? So when we add a new song, we've already trained some embedding U, if we add a new song, there's no like natural way to add a new song, especially if that new song doesn't have playlist data, right? So either it's gonna have to be 0, like the embedding is just gonna have to be coordinates of zeros, because so far we've only learned on playlists, or we're gonna have to initialize it randomly, and then if we're using this to actually generate playlists on Spotify, it'll get like randomly assigned to random playlists, and then we have to like wait for users to start like adding the song to their own playlist before we can learn anything, right? So this is kind of called the cold start problem, and it stems from the fact, again, that we're learning from nothing but the labels, right? We're just learning from which songs are in which playlist. So the solution to this is to use some kind of metadata or some kind of tags that accompany the songs to help learn the embedding, help kickstart the embedding in the first place. So we can, if whenever Spotify, I keep saying Spotify doesn't actually use this, but I'm just using it for the sake of example. If Spotify receives a new song, usually it'll say who's the artist, who's the label, what's the label, what genre it is in. We can treat that as additional features and attributes of songs, and we can incorporate that into our model and incorporate that into our lower dimensional embedding. So yeah, we can learn an embedding of songs as well. So this is one way that this paper did it. So this is, again, none of this is like the correct way of doing it. We're just presenting the way that one research project did this. But we have not only the songs, the playlist, and the playlist definitions, but also the tags for each song. So now the learning objective becomes a little bit more complex, but again, it's just, I wrote down here, I'm pretty sure this is U given A joint T and not U given A joint T, but I'll clarify that on Piazza later. We should use parentheses in these expressions. It's not clear which commas and vertical lines are joined. But again, the point is that we're also projecting the, we're also learning an embedding for the tags themselves into a lower dimensional space, and then we can do the exact same thing that we did. One interesting, I should mention, that happened here is that they added the constraint that that the song embedding for a new song should be approximately equal to the average of the tag embeddings, right? So when we're adding a new song, we don't get an embedding of the songs themselves, right? And so when we cold start, we can kind of initialize with the average of the tag embeddings that it came with initially. And then we can update this as we get more data. Okay? But again, just the high-level takeaway is we can use additional metadata to help with this embedding space. Yeah? Kind of, yeah. That's one way to think about it. Yeah. Mm-hmm. Any other questions? All right. Oh, and you can solve using gradient descent. Again, that's kind of assumed at this point in the, we've talked about gradient descent so much in this class. You can always do this with gradient descent. Everything's convex. Everything's real pretty. Yeah, so now we can actually visualize the embeddings in this space. We can visualize the embeddings of the tags in the same space as the rest of the songs. So I think this is the average embedding of like the tag in this space, and you can kind of tell our NB and our NB are over here. It's just a syntax error, I guess. But you can kind of see, Christian and Christian rock are in similar spaces. Indie rock and punk are in similar spaces, right? It learns this embedding where similar genres are also near each other. Again, because this is a distance metric that we're learning. Okay, so this is just covering, now that we have the tags, how would you add a new song? You have no evidence. This new song S prime does not appear in the corpus at all, but we have the tags, so we can initialize the embedding as the average of those tags first, and then we can update them further. So at least we have some reasonable place to start the song embedding as, and then as we get more data, we can update the actual song embedding based on the playlist information. And then this is actually, apparently, implied from the objective function itself. I will leave you to derive that from the paper yourself. All right, that is the last time we're going to talk about songs, at least for a bit. Everyone good on the song playlist embedding stuff? Okay. It's pretty straightforward because of the Markov assumption as well. Like the task itself is pretty straightforward. You have these previous songs, predict the next one, right? And then we assume that each one is just on the previous one. And again, the lower dimensional embedding space lets us do this semantically instead of just based on like individual song IDs, instead of using a lookup table. Okay. All right, let's switch gears and talk about word embeddings, which, again, I suspect most of you have some background in just because it's been so popular lately, especially with ChatGPT. But the idea is, in this case, given some large corpus, so Wikipedia, you can download the entirety of Wikipedia onto your computer with the click of a button if you want. But you can do that. Also, like Google News is a news aggregator, so it's a pretty common corpus. There are tons of corpus data sets out there. You can do Wikipedia. There's like a Reddit database. There's like a BBC News database. There's a ton of these data sets out there that you can do it with. And they all have their kind of idiosyncrasies, right? So like you can imagine that the language used on Reddit is very different from the language used on Wikipedia. So that will influence the kind of word embedding or model that you train. But anyways, point being, there's a lot of these examples out there. And so we want to learn a word embedding to model sequences of words. So you can almost imagine one possible way of doing this is the same thing in the song sequencing task where we say, this is the sentence so far, what's the next word, right? And that's almost what your keyboard is doing on your iPhone or your Android, right? Like predictive text where it kind of suggests what word should be next. And then there's that fun game you can play where you start with a word and you just keep pressing the next prediction and it generates some weird sentence, right? That's basically what this is doing. So as we get into talking about word2vec, we need to switch gears from capturing semantics via distance into capturing semantics via inner product. So the difference here, again, is that before we were embedding songs into the coordinate space and we were saying that the Euclidean distance between 2 points is what defines similarity. But now we're saying that it's the dot product, it's the inner product of 2 vectors. We're going from treating these embeddings as points on a coordinate space to vectors with directions, and we're projecting like vectors onto each other to define similarity. How's that any different? So first off, this is basically just a latent factor model because that's how dot products work. And then also there's
you always like take a point of vector.
You can. So you can take an embedding that's a point and then use it as a vector later on. But I think specifically for word2vec, this setup gives us some mechanical benefits. And we'll kind of go through that and see if by the end of the lecture it kind of makes sense. If not, come back to me and then we'll talk about it. Okay, so kind of visualizing this in the space previously as we did before with the circles. This time, we have, we're learning this embedding U and V. We're representing them as vectors starting, as a direction starting from the origin. And then the inner product, we're projecting each of these vectors U onto vector V. And so any vector that projects onto these lines, right, are similar probability. So instead of the concentric rings, now we have these dotted lines because we're taking the inner product of 2 vectors. And then again, and thinking about this back in the song space again, in the same exact way, we only have to learn 2 k parameters per song and 2 cardinality s k parameters total. Same thing with the word embedding as well, right? So we have the same computational complexity. We're just kind of interpreting these vectors differently. Okay, so what is this? Okay, so one way to do this, and again, setting up this problem exactly the same way we did the song playlist problem. One way to do this is say we have words, we have sentences, and we have, right? So we have the vocabulary of all the words that ever exist, right? We have our dictionary. We have our list of sentences, and then for each sentence, we have some sequence of words. Again, order matters, right? And so the learning goal, again, is in the maximization form, we're finding some projection U, right? We're finding some projection U and V such that we're maximizing this likelihood, the probability of each observed sentence. And then this gets converted into negative log, minimizing the log negative likelihood. You'll notice that we have U and V here still because a word, we're assuming that two words in a different order are different. So the after dog is different from dog after the, which does make sense in the English language. That's actually a correct assumption to make. And with the playlist, it was a little shaky, but at least with languages, we do know like a word coming after a word is different from a word coming before a word, right? So that's all we're getting. We have the entry point and the exit point embeddings per word. So this is what you would do if your task, so this is kind of interesting. Let me make this segue. So this is what you would do if you were trying to make, if your task was to predict the next word in a sentence, right? So if that's what you were trying to do, this is how you would set this problem up. But with Word2Vec, what we're actually trying to do is we're trying to learn a good embedding, right? So we're trying to say, so that we can use these embeddings for all kinds of different tasks down the road, we want to set up this problem in such a way that the embeddings that we end up with in the end are the most informative and contain the most semantic information. You can see how those things are different, right? So for the song sequencing task, the embeddings arose out of trying to accomplish a task, of trying to learn some playlist model. And out of that, we got an embedding, and maybe you can use that for something else. In case of Word2Vec, the intent originally is to learn a good embedding, right? And the task is just a vehicle for us to learn that embedding. And that's where the skip-gram model comes from, and this is what Word2Vec uses. For a skip-gram model, we're not trying to predict that a word will come after a previous word. Instead, for some given word, we're predicting the likelihood that some other word is within some window length C of that word, right? So again, given some word, we're predicting that some other word is within some skip length. So 3 words after, or 3 words before, or 2 words after, 2 words before, etc. And we're multiplying all of it. Okay? So for some sequence, for some sentence, we're looking at each word, and then we're looking at some skip distance away from that word, and we're saying, what's the probability of another word, right, being at that skip length? So for practical, from a task standpoint, this is nothing, right? Like we can't accomplish anything with this. But from a learning a good word embedding standpoint, this actually lets us learn the relationships between words. And it lets us do this at a further distance of words from other words in the sentence, right? So you can imagine, and we'll go through an example, but before we had this first order Markov assumption that each word only depends on the previous word, which is great for generating new playlists, or for like suggesting new songs to new playlists and new users. But here we don't care about the actual task. The task is just a vehicle to learn the relationships between words and encode them within the embedding that we've learned. Right? Okay. So like n-gram models were a thing already before this as well. N-gram word embeddings being n words that are adjacent to each other, but the innovation here is that we're skipping, right? So we're saying, is this word 3 words away from another word? And turns out that really helps us learn semantics of individual words better. All right, so what are the benefits? I already talked about it a little bit, but let's talk about it a little bit more. So let's say we have 3 sentences. Your entire data set, let's say, is the dog jumped over the fence, my dog ate my homework, or I walked my dog up to the fence, right? If we just do the Markov assumption as before, we would only see that the word dog is related to the word my or the word the, right? So that's the only thing that the model would learn. But with the skip-gram, we can actually say, well, maybe the word dog is related to the word fence somehow, right? There's some relationship because it shows up twice in my sentence. And not only that, the model is able to kind of make these long distance relationships instead of just looking at adjacent words. And so that's the benefit. And that's kind of the, and that allows us to learn more complicated semantics than just, what word comes next. So here, again, the distribution of neighboring words is more peaked, if that means anything to you. And then also the distribution of further words are more diffuse. And then again, most importantly, you can capture everything in a single model. So previously you might do a n-gram model with some given n, and then train multiple models with different values of n, and then do an ensemble or something. Here, because of the nature of skipgram models, we can capture all of this in a single model. Okay. Any questions about skipgram? All right. So again, it's interesting because the task itself doesn't do anything for us, but it's designed in such a way that the model can learn the best embedding it can. All right, so far we've been talking about these embeddings, but we haven't actually talked about the dimension to which we're reducing, right? So what should k be? What should this what should the size of this lower dimension be? So if we set k to just the cardinality of s, so to your entire vocabulary, we're not actually doing anything, right? We're just assuming that we can memorize every word pair interaction. We can calculate that lookup table is what we're saying if we set k equal to the cardinality. Smaller k assumes that words lie in some lower dimensional space, and so we're assuming that some low rank matrix, that some lower complexity model, that some lower dimensional space can represent the similarity and the differences between words and the relationships between words, right? And that's what gives us our generality. And yeah, again, easier to generalize across words. If you use a larger k than cardinality s, which you would like never do anyways, but that'll like extremely overfit to your corpus, and it'll basically memorize all the sentences, which is not what we want. All right, let's look at some fun examples. So word2vec works so well, and I should mention the original word2vec uses neural networks for the embedding itself, right? So far we're talking about like, maximizing u or minimizing the objective function for u and v being like some matrix, right? Again, the actual nature of the embedding can be a neural network. So word2vec optimizes for this using a neural network embedding. The embedding is so good that we can do arithmetic with the words, right? So the words themselves have a vector representation. So now we've learned some vector embedding of each word. And if we add two words together, we get the semantic equivalent answer, right? So if we add the vector for Czech, which is a country, and then the vector for currency, then we get a vector that is very close to the same word vector for koruna, which is the currency of the Czech Republic, right? So again, you can do this similar thing where this table is showing the arithmetic that they did. So they added the vector for Czech and currency, Vietnam and capital, German and airlines, etc. And they're looking at what other words have the closest vector to the result, right? So this is the top 4 vectors close to that result. So, the top ones are the most likely, and then it gets less likely as it goes down the road. And some of these are wrong, right? Because it's not trying to learn like the correct answer, right? But just the fact that just using sentences, again, we just gave it Wikipedia, basically. And just based on text that we've written, it's learned the meaning, the semantic meaning of these words, and embedded them into a vector space in which they can be added and subtracted and manipulated with in this way. So yeah, like it knows that Lufthansa is a German airline. It knows that the Moscow River or the Volga River are like Russian rivers, and it knows that these are French actresses, right? So again, it's pretty impressive that it's able to learn this. We can get even more complicated. We can take the vector for France, subtract the vector for Paris, add the vector for Italy, and end up at Rome. Again, if you kind of think about it, that makes sense, right? We're trying to say, we're taking away the concept of a country, adding in the concept of a different country, and it knows or in the embedding space, it's similar to the actual embedding for the capital of that other country, right? So this seems to indicate, this is some empirical evidence of the fact that our embedding is correct, or at least our embedding is able to encode meaning of the words. Yeah.
I'm not 100% sure I follow. I feel like if it was like Paris minus France.
Well, so if you have France minus Paris, so we're taking country minus capital city, right, and then we're adding another we're adding another country. So then we're so you can say vector of France minus vector of Paris is like the vector of capital city, right? And then the vector of capital city plus Italy, you get Rome. So this isn't exact, right? Like, yeah, I mean that's fair. But like, if you go through this paper, there's a ton of these other examples, and these are other examples as well. And sometimes it's wrong, right? So it thinks copper. If you take this relationship vector between copper and Cu, which is the elemental sign, it gets zinc and gold correct, but it then relates uranium to plutonium, right? So it's not perfect, but again, the embedding space is good enough that it does pretty well on a lot of these. Here's a 2D PCA projection of countries and cities. So we take the embeddings for countries and the embeddings for cities, and we draw lines between them. And a two-dimensional PCA representation of this, we can see they mostly point in the same direction. So it's learned this, and this is an incredibly high dimensional space. So it's hard to think about this. But if you project this into PCA, you can at least see it's learned the same relationship between countries and their respective cities. And yeah, so that's cool. That's, I guess, the point, is you can do this with Word2Vec. This has had major implications for everything. For this kind of work, for translation, this has been a huge work, because you can take an embedding of a sentence in one language, and then the embedding of a same sentence in a different language, and they'll be on the same space, right? Because it knows the meaning of both sentences. And so that's how Google does translation mostly now, is with like feature embeddings of words and sentences. Because they can take two sentences in different languages and then embed them into the same space. And then you can jump between languages that way. Yeah. So again, major implications for NLP in general. Okay, as a quick aside, you can use these embeddings as features for any downstream task, right? So you can use whatever U or V that you've learned, and you can use them for further machine learning down the road. You can just call this like feature extraction for machine learning. You can kind of call it transfer learning. It's not really that way, but like task transfer is like another way of doing this, where we learned one thing initially, but we use the embeddings learned from that to do something else. The benefit of that is that you don't have to learn everything every single time, right? So we can say some other model has already learned what words mean. Now it can do other more interesting things with that, right? So one thing might be sentiment analysis. So for example, is this Google review a positive or a negative review, right? I don't want to have to load in every Google review and learn this from scratch. But if I can embed all the sentences into some embedding that someone's already trained on, like Wikipedia, now I can just use those vectors and just do linear regression on vectors to do like sentiment analysis, see, and like classify positive, negative, right? So it takes a lot of load off on the computational side. Okay. You trained Word2Vec with gradient descent. I don't think I need to talk about that anymore. Again, Word2Vec itself uses a neural network for the embedding, but you can really use anything, but neural networks are the most expressive, and you can give it like a massive dimensionality thing. All right. Just a few more slides left. Ooh, okay, this is fun. All right, we're going to talk about this real quick. So this is so we talked before about when we do this denominator is really expensive, right? So in order to normalize whatever top part you got into a probability, you need to divide it by like everything else, right? So for first order Markov, to get the probability of one word happening after another, you have to get the probability of every other word also happening after that word and then normalize by it. This is really expensive, and so you need to solve this. The way Word2Vec solve this is with a hierarchical approach called a probabilistic decision tree. I prefer the paper calling it hierarchical softmax, because you're doing softmax but with a hierarchical tree. This is also just like Huffman coding, right? So if you're kind of familiar with that, you'll kind of recognize that. But the idea is, instead of having to calculate every single one, we use some binary tree structure to represent our words instead. So at each stage, right? So each of these leaves is a word, right? And then we're saying that instead of having to calculate all of these conditional probabilities in order to do our denominator, our normalization, instead we can learn just this arrow, and then just like each of these arrows in this hierarchical tree. And then that means that our complexity to arrive at one of these leaves, we don't have to do every single one. We can just calculate the path to each leaf in this tree. And the way this is set up, we can actually guarantee that all of the leaves sum up to 1 in the end, the way this is set up. Again, read the paper if you're interested in that proof, but just take my word for it. So again, so the probability of this word occurring after some other word is this probability combined by this probability, right? Yeah, so it becomes a collection of binary logistic regression instead of this massive multi-class logistic regression problem. And we can, again, so in order to do this, we actually need to estimate the embeddings of these internal nodes as well, right? Because we need to learn this conditional probability and we need to learn this conditional probability. So what this is doing, let me see here. What slide is this? 57. Next one. Okay, so what this is doing is now we're improving our computational efficiency, right? Because again, we don't need to calculate every single one of these leads all the time. We just need to follow down one of these paths. But it also means that we're increasing the number of parameters, right? Because now we need to learn the embeddings of these internal nodes as well. And so we need to learn more. The model has more parameters that we need to learn. But when we actually run the model, the computational complexity goes down. But one consequence of having more parameters to learn means you also need more data in order to actually learn like an equivalent model. So this is a kind of a trade-off that you'll see a lot when you do these kind of problems where we can reduce the computational complexity, but you need to learn more parameters and you need a lot more data to learn that. But yeah, it's just hierarchical softmax. We're just taking advantage of the structure of binary trees in order to make it faster, but we need to learn more parameters as well. Okay. And we just do it with gradient descent. And so because of that, the complexity goes down to O of base 2 log of the cardinality of S instead of O of log S. Instead of instead of big O of S. We can do big O of log base 2 of S. Okay, so as a quick summary, this is just hierarchical softmax. This is one way you can solve that normalization factor being too difficult to calculate. Yep. Yeah. Each word is a leaf, and then because words share these kind of different layers within the trees, it's more efficient. All right, so kind of wrapping up this section, and then we're going into deep embeddings, and we can get through that pretty quick. But it's pretty fun. But again, this previous song embedding that we have is a distance-based embedding, right? So we're defining the similarity of 2 points as the Euclidean distance, right? So that means that the semantics become clustering and locality, right? So similar points are in similar locations in coordinate space. But the axes become difficult to interpret. It becomes difficult to assign meaning to the axes themselves. Instead, it's just like what's close to each other. But the actual axes of the clusters themselves, we can't really ascribe any like post-hoc meaning to. But it's very easy to visualize, right? We can just do a 2-dimensional t-SNE or a PCA dimensionality reduction, and we can do these clusters very simple, pretty straightforward. The inner product embedding that we did in Word2Vec, where the similarity is measured as the dot product, the semantics are now rotational, right? It's the direction of the vector that really matters. And therefore, we can ascribe semantic meaning to the axes themselves, right? So we can say this axis is, I don't know, like the relationship between a capital city and its country or whatnot, right? Like we can go in post hoc and say, oh, this axis looks like it's covering this or this or this, etc. But that also means when we plot it, we can only do 2 axes at a time because of the 2-dimensional nature of our visual cortex, I guess. Or you can do 3, and I guess you can make an animation of like this 3-dimensional plot spinning on your plot, but that gets pretty complex. So that's kind of the difference between distance and vectors. Does that kind of make sense? So it's less so that one works better than the other, and more so like what are you trying to do with the thing that you got, right? You can also imagine in Word2Vec, if you had done Word2Vec in this space, you wouldn't really be able to like subtract and add vectors together because there's no sense of direction anymore, right? It's just similar things are near each other. So the relationship between words is just they're in a similar cluster, not the relationships like go in directions and you can add and subtract. All right, so the last part, in the last 5 minutes, let's just go through deep embeddings. So as I've mentioned before, we've kind of talked about embedding problems at a high level just to set up the structure, but obviously you can do this with deep learning. And we've covered this example before in the last lecture, but this is the clothing style embedding project that we talked about. So the goal of this project is to say that some clothing items are kind of fashion compatible, right? Yeah, so style compatible, like some clothes can be worn together and some clothes can't be worn together. And so the training data that they got is they scraped Amazon, and basically every time you like click on an item on Amazon, like a clothing item on Amazon, it also says frequently bought together, right? So it says other people bought this shirt with this shoe, right? They're ascribing the meaning of style to that. There's obviously no guarantee that people always buy like stylistically similar clothes on Amazon. In fact, who buys clothes on Amazon? Really, right? But for the sake of this project, and I think this is pretty early as well, let's just say that the frequently bought together means that two clothing items are stylistically similar. So then this training goal that they're trying to learn is we're trying to learn some model parameter such that given some embeddings of images, and we'll talk about this, similar stylistically compatible images are encouraged to be near each other, and stylistically incompatible images are encouraged to be further apart, right? So this L plus and L minus, it just means they're loss functions that encourage the embeddings to be nearer or further apart based on whether or not they're compatible, right? So that's all we're saying. So how do we get the embeddings of the image? We can actually get the embeddings of the image from a convolutional neural network. So we talked before about how using CNNs we can do image classification and such because we're ascribing this like spatial invariance, right, et cetera. But at the end, we had this logistic regression layer where we got the class, right, where we said, is this a dog or not? But if we actually just chop that off of an already learned network and we just take the activation values of a single layer, we can treat this as an embedding. And it works really well, like surprisingly well, like unreasonable. There's a paper called The Unreasonable Effectiveness of like feature extraction from deep learning models. So even though the final task was to classify between 1,000 classes, we can take some arbitrary layer in this network and just use it as a feature representation, as an embedding of the image itself.
It doesn't matter which layer. I always thought you wanted to take the second to last.
It does depend on what you want to do. So theoretically, the later layers contain more semantic information, and the earlier layers contain more kind of pixel-wise information. I have a research paper where I say that's not true, but generally you would take the second to last layer or something like that. Yeah, depends on the architecture as well. Yeah. Okay, so they're going to refer to this as a Siamese convolutional neural network. So they're going to take two of these neural networks. One's going to run through one of the pictures, the other one's going to run through another, and then we're going to calculate the loss function between the two. And then when we do gradient descent, the gradient flows through both CNNs, but these are identical. So the weights are updated on both whenever this like gradient descent goes through. So again, we have some CNN that's already giving us the embedding of this image. We recommend that compatible clothing are near each other, incompatible clothing are far from each other, and then we just do gradient descent, right? Which is kind of, it's fun that we can kind of do this in an end-to-end kind of a way. So some minor details on the training. So first, turns out you want this embedding dimension to be smaller, because if this dimension is too large, I think they used AlexNet for this. And so AlexNet has two fully convolutional layers at the end of dimension 4096, and then the final classification layer, which is 1,000. But turns out 4096 is way too large. So you need to, within the neural network, add another 128 layer just to get the dimensionality down to 128, and that works better. Also, I should mention that they're using a pre-trained model. So the CNN doesn't start from scratch. It's originally trained on like ILS VRC 2012, which is the ImageNet 2012 challenge like dataset. Very popular computer science computer vision data set for initializing like a CNN, right? So you start with a CNN that has learned some features, and then you train it even further to do this particular task. And then finally, you'll notice that when we scrape Amazon, we only get compatible pairs. We don't get incompatible pairs, right? Amazon doesn't say, you bought this shoe, please don't buy this jacket, right? Because it only tells you what other people bought. So you need to sample your pairs correctly so that in your training examples, not only do you have compatible pairs, but you need to artificially generate these incompatible pairs by taking random pairings of data. So it's possible that this is noisy, right? It might, you have some chance of accidentally randomly picking two items that are in fact compatible, but we're kind of betting that even if we do this randomly, even if the labels are a little noisy, we'll get enough signal to be able to train this model. All right, so finally we end up with, so here's the embedding. So this is a two-dimensional t-SNE of like the embedding that they came up with. So in this embedding space, you still get kind of similar things in the same region, right? So you don't really see the compatibility here. When you do t-SNE, there's some nuance here where it'll kind of prefer to put similar objects near each other, but you can see that in some of these spaces, there's different articles of clothing in the similar region as well, right? So like, yeah, like all the watches are compatible, sure, but that doesn't really help us, right? But at least over here, like you get some hats and some jackets and shirts, and these all seem to be like children's clothing, etc. So using this, now we can suggest outfits. So we can say, given these green boxes, we recommend these pants and these shoes, right? So again, this is completely based on the frequently bought together, and so we won't make any judgments on the actual stylistic tastes of Amazon purchasers, but you can at least see, it pairs kind of semi-professional clothing with, I don't know, heels, or like sports clothing here with like sports pants and like flip-flops, I don't know, right? But it's at least better than random. If you kind of squint, at least based on the fact that it's only seeing the images, right? And we've only given it Amazon pairings, it's pretty reasonable. All right, this is the last slide. So as a quick recap, again, embeddings, given some training data, we care about some property of the training data. For the song embeddings, for the playlist embeddings, we talk about the Markov chain, this first order Markov assumption. For word2vec, we have the skip-gram formulation. And then finally, for the fashion style model, we have the affinity of two items to be purchased together, right? So we can build some structure around those semantics to then learn the embeddings to be able to do these, encode these semantics within our embedding space, right? So again, the goal is to learn some lower dimensional representation. And again, it doesn't have to be lower dimensional, right? We can set the dimensions to be equal or even larger. It just happens that in most problems, our data tends to be much higher dimension than the actual number of dimensions that's required to capture the variability and the qualities of the data set. So we call this an embedding. We get a lower dimensional representation of our data that also reflects the semantics that we care about, the similarities and the differences that we care about. And we kind of covered 3 different ways to express that similarity. We have the vectors, we have the coordinate distances, and we also have pairings, right? We also call this metric learning a lot of the times, where we say, I'm going to give you a list of all the things that are similar and all the things that are different. You learn the embedding for me to be able to do that, right? Yeah, so the geometry itself captures what we're interested in. And again, very, very powerful tool for representation learning. There's an entire conference just for this called ICLR, International Conference for Learning Representations, right? It's a major machine learning conference. And again, very useful for downstream supervised learning tasks, and it actually makes deep learning actively more accessible for other people, because you don't need a GPU to train your own model. You don't need 2 terabytes of data to train your own model. You can take this pre-learned model that some other institution has already provided that has already learned this embedding, and now you can do some downstream task. You can transfer learn, and you can, I don't know, learn to do other things with those useful embeddings that we've learned. So this is a huge field. Even specifically for NLP, we have moved past word2vec into something like GloVe, which provides additional corpus level global context, and most recently BERT, which is in 2019, which is BERT, and that uses transformers, which I'm sure you've heard a lot about already. That's what like ChatGPT is built off of. It's just a recurrent network with attention mechanism. It's very interesting if you want to kind of read into that. That's worth it as well. If you're interested in NLP, this is your life. It's just embeddings, right? And then everything else also eventually ends up being embeddings. So this is a huge field. It's very useful, and it'll be especially useful as we move on to probabilistic models and naive Bayes. There's also a probability recitation coming up. I realized that because we changed the schedule, it's a little late. It happens like after all the probability lectures and like the homework. So I'm going to ask the TA if we can like shift that up, but if not, it'll still be useful for building like your probability bases to be able to do the homeworks and like understand the rest of the lectures. All right, thanks. Sorry, 5 minutes over. Still working on that.